Hello guys again, and this is a review of trigonometry. It's something that you were presumably supposed to know from before, but let's at least go through part of it. I can teach you, I think, all of trigonometry in 6 hours, everything that you need to know and know well in 6 hours, but I don't have all the 6 hours. And so here, first question guys is this: how many degrees are in a circle and why? And let me if you quickly can respond. If not, then I'll just tell you. Yeah, 360, but why is the interesting point. So many of you remember the 360 stuff, but why is it 360? And what do the 360 things, 360 degrees supposed to signify? So let me tell you, it's actually very simple. It's absolutely arbitrary. There is no reason why it's 360 other than the fact that Babylonians were fond of base 60 numbers. And what are base 60 numbers? Like we have base 10 numbers. Maybe because we have 10 digits, right, on our heads. Maybe because of that we have 10. So at least it seems intuitive to me that we would have 10 fingers. So what is the base x system? The base x system means that if I take an integer x, then it's a polynomial where each coefficient of the polynomial is a number between 0 to x minus 1. So here is an example. We have 153 in base 10 system, guys. In base 10, it is 1 times 10 squared plus 5 times 10 to the 1 plus 3 to the 10 to the 0. You understand? 1, 5, 3. Each of those numbers, the coefficients, instead of x, I have 10 here. So it's a polynomial, but we call it base 10 because you see we have base. It's like the base of an exponential here. 10 squared, 10 to the 1, 10 to the 0. Make sense? So or the number 33.533 is what? It is 3 times 10 to the 1 plus 3 to the 10 to the 0 plus 5 10 to the minus 1 plus 3 10 to the minus 2 plus 3 10 to the minus 3. Do you understand? So you're using base 10 in that sense. Now, if I wrote 153 in base 9, 153 in base 9 will mean 1 times 9 squared plus 5 times 9 to the power of 1 plus 3 times 9 to the power of 0, which if you translate to base 10 is 129. Good? That's what this means in base 9. What about 153 in base 6? That's 1 times 6 squared plus 5 times 6 to the 1 plus 3 to the 0, which if you translate to base 10, it's 69. Are you getting it, guys, so far? What is base thing? It's not so important, but I just wanted you to understand that we have a base 10 system, but the Babylonians had a different base that they were using for their calculations. Do you understand? Write in the comments if you follow what I'm telling. It's pretty simple, I hope, right? So base 10 you all know, and then you see that it's arbitrary. Why use base 10? We can use another base. We're just used to base 10. That's the convenience. Good. So 360, it's in base 10, right? In other words, when I say 360, usually without mentioning the base, I'm assuming this is base 10. What is it in base 60? It is 6 times 60 to the power of 1 plus 0, 60 to the power of 0. So it's just 6 in, so it's just 6 in base 60. You understand? In the Babylonian system, it's like the numbers, it looks like the number 60. And they were very fond of the number 60 for reasons that I do not know. And what survived from Babylonian times is that, you know, this 1 hour is 60 minutes. Have you thought about it? 1 hour is 60 minutes. Why is that? And 1 minute is 60 seconds. Why is that? Do you remember the clock? That's how clocks used to look like, guys. You see? They were circles. And Babylonians had, well, they dealt with circles. The 360 stuff, it has to do with circle. Do you understand? And it's actually 60 in base 60. So I think that's pretty much why we kept that from the Babylonians, the clock. Good. Now here is the next question, guys. What do degrees measure And how do they do it? How do they measure what they are supposed to measure? Can you figure out? Can you tell me? Measure angles. Good. So Steven says they measure angles. And what is an angle, guys? A part of an arc, possibly, but here is what I think of an angle, guys, right? So an angle is, if you look at a blade, right? Take a blade of a knife and you ask how sharp it is. So the angle is supposed to measure this sharpness, this edge, right? So if something is dull or something is sharp, if the angle is acute or obtuse. So something that so it measures corner or the sharpness of a wedge. Now here are what degrees are, guys, right? So how can I measure that? Imagine you take a pizza pie, and you slice it into 360 equal slices. You understand? I mean, you like pizza. You live in New York. New York has well, used to have, and I'm not sure what it has, right? Used to have pizza that you sliced into 8 pieces, right? So if you sliced it into 8 slices, then of course it's just a bit gross. It's not, you cannot do too much with 8 slices, but that's a measurement of angle, right? It's not degree. It's call it 8 Italians or 8 slices, something like this. What do you call it? 8 Italians or 8 pies or something. You understand that you can create a different measure. But if you cut it into 360 parts, the slices are very thin, and you can describe quite a lot of things with such thin slices, right? So they're thin and sharp. So 1 degree is 1 slice out of 360 in the pizza. You understand? You're counting the slices. 2 degrees are 2 slices, etc. Does it make sense? So how sharp is an edge is basically, you can imagine extending this edge to, you just look at this tip of the edge, extend it, and make it look like a circular sector, like a slice of pie, right? And then see how many 360, how many of the 360 slices will fit along it. Okay, so that's the idea. You see, here is a wedge. This is less sharp than this wedge. You understand why it's less sharp? Because it fits 3 slices of pizza, 3 of the 360 slices. This one fits 2 slices. Are you with me, guys? So think of degrees very much like you think of slices of a pizza. And of course, degrees are not natural as units, you see, because there is no mathematical reason, there is no logical reason to cut a pizza into 360 slices. You could have done it into more slices, less slices. You see, you would have other measurements. It's not a natural measurement of an angle because of that. Make sense, guys? Because in other words, aliens would come around and they would not measure the angle the same way, because even if you say you measure angles using circular sectors, you still don't give reason why you need to slice the pizza into 360 slices. So a circle has 360 degrees arbitrarily because it was decided to cut it into 360 slices instead of the usual 8. Good. And then the next question is, of course, is there a natural measure of angles? And that happens to be the radian measure. So Archimedes discovered the following property, that the circumference of the circle is 2 pi r. What does it mean, guys? 2 pi r. It means that the circumference is 2 pi multiplied by the radius. Or it better said is that if I take a radius, okay? If I take a radius and I fold it around the circumference, I will always find that I can fit, folding around the circumference, 2 pi copies, which is slightly over 6, you understand? 2 pi, if you simplify pi is 3, 2 times pi is 6. So essentially you can fit a little over 6 copies of the radius folded around the crust of your pie. And you see, here is the idea, right? So if the radius is of, let's say this is 1 inch. If the radius is of 1 inch, then you see you would have a smaller pizza, but still the pizza will contain around its circumference will contain the length of slightly over 6 radii. If the pizza is larger, doesn't matter, right? The radii are larger, but still the larger radius will be folded around the pie crust about 6.2 something times. Make sense? Are you with me so far, guys? I will draw. I have another drawing for you. See, I spent this time drawing this crop for you, so I hope you actually understand it finally, right? So so 2 pi is 6.28, roughly 6.3, right? It's not a true measurement. It's actually, the true measurement is irrational. We'll talk about that later. Here is again, here is the same information, guys, right? So what is the 2 pi r? If r is 1 inch, then circumference is 2 pi or 6.28 inches. If r is 2 inches, the circumference is 2 pi multiplied by 2 inches, but really 2 pi times radian length, radius length. So it's 6.28 copies of the radius. Are we clear? Here is the picture unfolded, guys. You see, this is the crust of a pizza, and I divided it essentially roughly into 6 parts. So what is the 1 radian, guys? The 1 radian is like 1 radius. Okay, here is 1 radius, here is another radius, here is another, here's another, here's another. So basically, when I lay them down on the x-axis, I get this. Do you see this? I get this red piece, this, and then the extra part is the 0.3 part. Are you with me? So this from the origin all the way to the right edge, that's the length of my crust in radius units. So make a radius bigger, the units will be farther apart, but you will find that the circumference can fit about 6.3 radii. Are you with me? Confirm, please, guys. I mentioned this, so you understand this. Here is a simple comprehension check. The degree is a slice, right? So let's say if I say I have 5 degrees, guys, in the comments, if I say 5 degrees, what am I really talking about? I have 5 degrees. It means, what did I do? Well, not necessarily to the left, but simpler. See, guys, it's a very simple question, right? Can you understand? You understand what I'm talking about? I have 5 degrees. Yes, the 5 degrees sharp. So you might say I ordered 5 slices out of this Babylonian pizza. Make sense? When I say 5 degrees, I ordered 5 slices out of this Babylonian pizza, and I can put them one next to another, and I have a wedge. I have one super slice containing those 5 sub slices. Good? 5 degrees sharp. Guys, everybody understands what I'm talking about, right? I mean, degrees is pizza. Now, if I say I have 1 radian, right? When I talk about radian, I have 1 radian. What am I saying? So if degrees, they talk about slices, then radians talk about what? What part of the slice? Crust, Dragon, beautiful. Crust, my God, you haven't been eating pizza in a while, right? Losing weight. But hopefully not from your brain. It's supposed to be a pretty heavy organ. It is crust. Okay, so here is what you should think, guys, right? So here is a pizza. This is let's say it's a pizza of I made it have 2 slices. Let's say those are 2 degrees, 2-degree pizza. Of course, it's much bigger than 2 degrees, but doesn't matter, right? I just let's say that's 2 degrees. So that means my slice contains 2 sub slices, and then how do I describe this angle? Look at it. The bigger the slice, the longer is its crust. But I measure it always with respect to the radius. Right? You see, because if the pizza, if the slice is much longer, then the crust will be longer. But that doesn't matter. By the Archimedean property, the circumference always contains the same number of radii. You understand? Just the radius is bigger, but circumference is always the same radii. Okay, so 2 degrees in this case corresponds to, I'm not sure yet what it is, we were going to verify, will correspond to S radii. You understand? So if I measure, if I say I have 2 slices and I want to convert it to radian measure, I just have to ask myself, what's the length of the crust in terms of the radius? What is that length? Are you understanding, guys? Right? So how do I verify what that length is? So then let's talk about the relationship between radians and the crust. So we know that 360 degrees, they carry 2 pi crust radians. Make sense? I wrote 3 bars. Because I mean, I remember even me when I was in school, I thought, but 360 is not equal to 2 times pi. I didn't understand what they were talking about, right? So they said 180 degrees is equal to pi. I couldn't understand it. Like, what do you mean? 180 equals to 3.14? But what they meant is this, that they measure the same thing. It's like 1 kilometer is the same as 1,000 meters. Do you understand? So I to indicate that that this is a relationship, they describe the same thing, I use triple bars here. 360 pizza slices carry 2 pi radius units. Are you with me? Now, if you are with me, tell me how much does 1 slice carry? How much crust in radius units does 1 slice carry? 1 Babylonian slice, to be precise. Thank you, Lakey, and the rest of you guys. Come on, come on. Are you alive? Participate, please. One Babylonian slice, how much crust do you get? One Babylonian slice, how much crust, guys? Do you understand this relationship? 360 slices carry the full crust of the pizza pie. Careful, careful, guys. 360 slices carry 2 pi, or roughly 6 point. The full pie carries the crust equivalent to the to 6.28 radio units. Actually, not that amount, but just roughly, right? 6.28 is roughly what it is. It is exactly 2 times pi. How much is carried by 1 slice? How much crust is carried by 1 slice? Yes, thank you, Rivin. Thank you, Hu. Thank you. It's a simple question, guys, right? You have cut a pizza, right? So if the full pizza carries 2 pi radians, you understand what radians are again, guys? Radians are just the crust. How much is carried by 1 Babylonian slice? How much of the full crust is carried by 1 Babylonian slice? 2 pi over 360. Beautiful. Do you understand, guys? It's so simple, right? the crust, they add up. They are, each slice carries the same amount of crust. 360 of them will carry the crust of 6.28 or 2 pi radians to be precise. Good. So that one means that one slice, you see 1 degree, you understand, that's just the code. One slice, it's 2 pi over 360 radians, which is pi over 180 radians. You understand? I divide by 2. Pi over 180 radians is one slice. So it's very little. It's 3.14 divided by 180. It's a small fraction of a radius. It's a very thin crust. You understand, guys? So you understand the idea of radian measure, right? So it's a natural measure because what? Because it's a property of the circle that the circumference is always 2 pi times the radius. So it's not arbitrary in that sense. It's that it uses an intrinsic property. So for time, for example, when you use atomic clock, you are using some oscillation of an atom. Do you understand? So that's what you mean by natural. It's something that it occurs in nature. Yes? Oh, great, Alexa. It's nice to see you. Are you following me, guys? And now let's see how I want to quick conversion, guys, right? 2 degrees, 180 degrees, 120 degrees, 60 degrees, 90 degrees, 45 degrees. Before you actually answer this question, tell me, guys, please, what am I asking? Convert degrees to radians. I want a nice explanation, not some sort of technical. What am I asking you? 2 degrees, I'm saying convert degrees to radians. What am I asking you? When I talk about degrees, I talk about slices of pizza, Babylonian slices, yes? And when I say convert to radians, what am I asking you to talk about? Exactly, convert slice to crust, beautiful. Basically, I want to know how much crust I'm getting in radian units. So this you should be able to do fast, guys. You see, I'm going over prerequisites, right? So that's theoretically something that you learned in other classes. Thank you, Sumaya. Well, you can establish that formula, Alexa. That's exactly my point. Here is just think about it. Very simple idea that will give you the formula. If you know what you're talking about, it's easy to convert one from the other. Okay, guys. So let's look through the examples. If you don't know how to do that, or you don't do it fast enough, stay after class. We discuss it and do it slower. Okay. It's again prerequisite for this course. I have little time. So the idea is very simple, guys. What is it? 2 slices. How much crust do they carry? It's very simple. All you have to remember is that 360 slices carry 2 pi crust. So that means that one slice carries pi over 180 of the crust. That's how much of a radius it carries. So 3.14 divided by 180 is the length in radius units of the crust. So 2 degrees is pi divided by 90. 180 degrees is pi, because 180 degrees means what? Means it represents the angle that of a line. You see, do you remember, guys? 180 degrees is the angle of a line, because that means that I took my pi and I took half of it, right? 180 degrees, it's half of 360, which means half of a pi, and that's a line. And that means I have pi, or 3.14 radius units along my crust. Make sense, Alex? All right. So it is just you're asking how much crust do you have in radius, right? So 180 slices bring 3.14 crust, right? 120 degrees, 120 crust, it's 120 times the crust of one slice. You see, it says I just add up the crusts. 120 pizzas, each pizza has this amount of crust, and then combined it's 120 times the crust of one pizza. You see how the formula works? It's very natural, right? 60 degrees is everything else is the same, you see. And 90 degrees is pi over 2. Pi over 2. In other words, it's slightly more than 1, right? It's 3.14 divided by 2, and that's because we have 90 copies of pi over 180 crust. 45 degrees is half of that, half of pi over 2, so it's pi over 4. Now conversion of radians to degrees works very much the same. I just think in reverse. How much does a slice that has crust of length 1 radius, how much does it bring? Make sense? So I know that the full pi has a crust of length 2 pi radii. That's why the radian measures, and that is 360 slices, right? So that means that if so what is one radius crust? One radius crust, I divide this by 2 pi and this by 2 pi. It's 180 divided by pi degrees. So that means 180 roughly divided by 3, slightly smaller than that, right? If I pretend that pi were 3, 180 divided by 3 is 60, right? So it's approximately, it's slightly less than 60 slices. You understand? So a pizza slice whose crust is as long as its side, so the length of the arc is as long as the length of the side, contains about 60, slightly less than 60 Babylonian slices. Make sense? So it's very simple conversion. I mean, you should be better. Exactly, it will be 57 point something. You understand? So, and it's an irrational number. You cannot fit all the slices, but essentially it's about 57 in some segments. You have to cut some of the slices into more pieces. Good. So before I ask this question, guys, the next one. So you should think in calculus in terms of radians. Degrees are arbitrary. Do you understand? They are not going to be good for calculus because you're describing nature. You understand? It's just the results are not as pretty, not as nice. So you will prefer to think in radians, and it should become natural to you, right? In other words, describe the angle in terms of the radius length of crust, right? Bigger pizza makes a bigger crust, but the relationship is just the bigger radius, you understand? So I just change my units. So radians are therefore unitless. Let me try to see if you understand this point. Guys, here is my circular sector. Here is a pizza slice. I would like you to tell me how many degrees are in this sector, given this information that this length is 3 inches and the crust is length 1 inch. Can you figure out how many degrees are in the slice? You understand what I'm asking? I'm asking how many Babylonian slices can I fit on this sector tray? Thank you, Joshua. And thank you, Yuzu. And how are you doing, Edwin Juarez? Thank you, Stephen. So just a little bit longer, guys, but come on, I want to see your answers. Yes, Alexa, right? So you always want to convert to radians, right? So see what it is in radians, and then you can convert it to degrees. Thank you, Zainab and Lisha. Great. Okay, guys, so let's do it now together. Yes, right. So give me the. Thank you, Edwin. Wonderful. Wonderful. I'm very happy that if you're getting it, guys, I'm extremely happy about it, right? So you see the 3 inches, it's not natural. Really, this means this is my radius, right? 3 inches are carried in 1 radius. Then that means that what is my angle in radian measure? This is 1 inch, which means it's 1/3 of a radian. You see? 1 inch is 1/3 of the radius length. That's what I really want to see. I don't care really that you measured it to be 3 inches. I really care this is 1 radius, and this is 1/3 of it. So that's what I do. I say 1 radius is 3 inches. That means that 1/3 of a radius is 1 inch, right? So that means that in the radian measure of this is simply 1/3. By the way, you use radian measure when you measure speedometers, right? When you're driving in your car, you're converting the speed of the rotation of the wheel into linear motion, and it's much nicer to do so using and thank you, Alexa. Wonderful, right? It's much nicer to do so using radian measure. Degrees do not naturally communicate to length of circumference, you see, because this is length of circumference in terms of radius. Much more useful in physics than degrees. People are just used to degrees, but this is much better. So so then we have 360 degrees is 2 pi radians. And remember, again, that's how, if you don't need to remember anything, just remember this, right? This is the only thing you need to convert, is that remember that 360 Babylonian slices carry 2 times pi crust. Good? So that means that 180 divided by pi degrees is 1 radian. And what we have is 1/3 of it. The crust is 1/3 of 1 radius. So it's 1/3 of that number. It's 60 divided by pi. And as some of you wrote, most of you wrote 60 over pi, and that's correct. And that's approximately 19 slices. Sorry, it's approximately 19 slices. That's right, right? 19 degrees means approximately 19 Babylonian slices can fit in here. Good? Wonderful. We're moving on, guys. Everybody understands? Polygons and angles. Now let's see, and let's try to do it in radians. What is the sum of angles of all the 3 angles of a triangle? Could you tell me, please? In radians. In radians, guys, we want to think in radians. Oh, the radians. Oh, you know the song, right? The radians. Pi. Okay. Come on. What about the rest of you guys? You know what is the sum of angles of a triangle? Can you guess my next question? Guys, so get, you see, 180 is wonderful, but get to think about radians, okay? So 180 Babylonian slices carry pi crust. Thank you, Etkin, right? They carry pi amount of crust, or roughly the equivalent of 3.14 copies of the radius. Now, can you guess my next question? So many of you wrote pi, and that's exactly what I wanted to hear. Can you guess my next question? You know me a little bit already, right? What's my next question? Maybe you don't feel you know me at all. Why does a triangle, its angles, why do they add up to pi radians? So when I was in high school, right, I never kind of mentioned it to people. I thought everybody knew, actually, right? So, but I figured one way to do it. The one I'm presenting is actually better than what I thought. Okay, so pay attention, guys. Here is a typical triangle. It has angles A, B, and C. A, B, and C, yes? And then imagine you're walking, right? You see, this is how you're walking. You're walking in this direction, then you turn around, you walk in this direction, you turn around, you go in this direction, and onwards, right? Are you with me, guys? You're just walking around this triangular park. Now, look at the outside angles. You see, so first you're moving in here. You understand? You're facing like what you know, where my arrow is pointing, right? This is where you're facing. You're looking straight ahead. Yes, you're looking straight ahead. Then at this corner you turn at a supplementary angle to B. Look at it. The angle here is 180. It's pi, right? This angle is pi because it's half of a line. But you turn some unknown angle. You turn it in here, and then you walk, and then you turn again, and then you walk, and then you turn again, and you're now facing the same direction. How much did you turn? When you make a full circle around this park, how much have you just turned? Forget about the distance you traveled. How much have you turned? Well, you made 3 turns, but I'm asking how many radians have you turned? Radians measure the angle, you understand? So so how much did you turn? You walked in a circle. Exactly. You turned to pi. Do you understand how I know that, guys? You executed a full motion. You know how you know you turned? If you're moving, if you're always rotating in one direction, and you end up facing the same direction that you started with. You understand what I mean? It's hard for me to show since I'm not with you. Look at it, guys. Right? I'm right now facing you. Yes. I can walk to the side a little bit and turn. I can walk a little bit more to the side. I turn. If I were moving, if I were turning always in the same direction, this is a counterclockwise direction that I was turning. Yes. And I end up facing in the same direction I started with, I made a full rotation. Right, first time from one time I was facing you to the next time I'm facing you, I made a full rotation. It doesn't matter that I travel some distance. Here I just travel a distance. That means I'm not turning. Here I try to illustrate. You see, this is the angle made by the line 1. This is the angle made by the line 2. This is the angle made by the line 3. You make a full rotation. Are you with me? This is the hard part. If you understand this, then I can move on. You understand what I'm saying? You just think about it, guys. If I whenever I turn in the same direction, and I end up facing the same direction where I started from. In other words, you see the direction along the line 2. You see, if I as I walk from here, I'm already facing this direction. When I complete my walk, I now am facing the same direction. That means I made a full rotation, which means in degrees, I turned 360 degrees. And in radians, I turned 2 pi radians. We prefer the radians, okay? Because they are more naturals, I hope. Do you understand? Right? There is no reason to cut a pizza into 360 slices, but the circumference of the circle is roughly 6.28 radii in length. Okay? And now I can make the following beautiful calculation. Look at it, guys. The angles A prime, B prime, and C prime are called supplementary angles. Do you understand? Because you can imagine extending the motion a little bit and then rotating. You can see that B and B prime are on this lying on a line, right? So I can easily calculate what's B prime plus B. What's B prime plus B? I don't know anything about B prime or anything about B, but the sum of B prime plus B is what? Yes, Lisha, exactly. But get to think about radians, right? What you said, but in radians it is pi. We need to excise this this intuition that you have. You're so familiar with degrees. You like to communicate in degrees. I want you to feel that pi or the radians are much closer to you. You know, you should get friendly with them. They are better. Good. So you all understand. So B prime plus B is pi. C plus C prime is pi. A plus A prime is pi. Everybody understands that part, guys? I have two observations. I know the sum of the outer angles, it's 2 pi. A prime, B prime, C prime, if I add them together, because that means I rotated entirely around the triangle, I got 2 pi. Yes? And I know B prime plus B, A prime plus A over them, right? So here is what I can say, guys. Look at it. If I add A prime plus A plus B prime plus B plus C prime plus C, what will I get? Each of them is pi, so I get 3 pi, right? If I just add those quantities together, it's 3 pi. But then I can separate and add all the primes together and all the non-primes. Yes, so we have this plus this is 3 pi. But I know the sum of the outer angles. The sum of those angles is 2 pi. So it's 2 pi plus A plus B plus C, which is 3 pi. And that means that A plus B plus C is 3 pi minus 2 pi, which is pi. I just very easily proved that the sum of the angles inside of a triangle is equal to pi. Was it difficult? Right? You see, it took us a few seconds. I hope you understand it. Do you understand it, guys? Because in a moment I will check it. Let me know if I can proceed to the next discussion. You understand that the sum of the angles in a triangle is pi, and that you can use this explanation. Would you be able to come up with this explanation on your own? So confirm, right? Yes, that you understood, and I will move on. Beautiful. Here is your next question, guys. Here is a polygon that has 4 corners. So it's it's a polygon having not 3 but 4 corners. I want you to tell me what's the sum of the inner angles. And I already actually helped you. I drew an assistance, right? Let's say you are walking counterclockwise around this park, and that's the shape of the park. I want you to tell me what's A plus B plus C plus D equal to. So calculate, guys. I mean, even if you can guess, that's not interesting. I want you to understand the idea. How did we figure out? Okay, how did we figure out what the sum was for triangles, and how can we do it here? Okay, good. If you can see the pattern, that's good. But I want you guys, I want you to understand the idea. How did I figure that thing out? All right, so let's see how we do that. Again, what is, guys, the sum of A prime, B prime, C prime, and D prime? The sum of the outer angles is what? You see how it is? You walk. Yeah, it's very simple to remember. You walk, and then when you make a corner, you extend a little bit the direction where you walk, and then rotate. Right? Walk a little farther and rotate. Walk a little farther and rotate. What's the sum of B prime, C prime, D prime, A prime, please? What's the sum of the outer angles? Outer adds to 2 pi. The outside adds to 2 pi. Do you understand why, guys? Because what do you do? When you walk around a closed shape, you are executing a full circle. Do you know how? It doesn't matter. You can turn many times or a few times. Look at it. I walk here, walk here, walk here, walk here. I always am turning in the same counterclockwise direction, yes? When I'm walking. Always counterclockwise, right? So moving against the clock. Now here, I turn up and I end up facing the same direction where I started, which means I must have executed a full rotation. You understand? That's like this. No matter if you track how I move, and only track if I face you again or not. And if I rotate in the same direction and I face you again, that means that I traveled a full circle. I rotated 2 pi. Good. So then I can do the same thing. The sum of those angles is 2 pi, and I can and the angles here are supplementary. In other words, you see B prime plus B, they add up to pi because it's on the line. You understand? Line is half of a circle, right? Line is like I cut the pi in half. So supplementary angles. So I use this information, right? A prime plus A, B prime plus B, C prime plus C, D prime plus D. It's 4 pi. So the summation here is 4 pi. And then I isolate A prime, B prime, C prime, D prime, and that's 2 pi. And then now I have sum of outer angles plus sum of inner angles is equal to 4 pi, but the sum of outer angles is 2 pi. So it means A plus B plus C plus D is 4 pi minus 2 pi, which is 2 pi. You understand? So the sum of the angles of any quadrilateral is 2 pi. What about, can you tell me what would be the sum of the angles of any polygon that has 5 vertices? What would that be, guys, in the comments? If I add up the inner angles of a polygon that has 5 vertices, what do I get? The inner angles. If I add up the inner angles, you can just give me the answer for 5 vertices if I sum up the inner angles. The outer angles, yes, you're right, 2 pi, but the inner angles, what do I get? Wonderful. You understand, guys? Isn't it easy? We figured out how to calculate the sum of inner angles for all polygons. Here is a picture. You carry out the same thing, and you get 3 pi. And in general, if the quadrilateral has n vertices, where n is bigger than 3 or equal to 3, the sum will be n minus 2 times pi. It's always the number of angles minus 2 multiplied by pi. So if you're curious, guys, this is not that's not at all it's a very profound idea, but even it relates to time travel, if you're interested in that. Is that, you see, already in the time of Gauss called it the Remarkable Theorem. He discovered that the property where the angles of a triangle add up to pi indicates that we're in a flat or Euclidean geometry. So if you were to try to measure a large triangle and find that the sum of the angles does not equal to pi, then you know that your space is distorted. And you can actually, it doesn't matter if it's a very kind of complicated, profound idea. It's like, you see, you imagine on a distorted space, you will not notice something, but it actually means it's distorted intrinsically. It's a non-Euclidean geometry. That intrinsically, it's a geometry that's not modeled by what you imagine space to be. And so those observations were in fact important for relativity theory. Based on relativity theory, you are saying that space is distorted. Again, this is known as Theorema Egregium, or Latin for Remarkable Theorem. Okay, so if you can Google it, you can read about it if you're curious. So yes, that has to do with understanding geometry. So if you see that my point is this: if you imagine that what you learned is nothing, you're very wrong. So here is the next problem we tackle, guys, is now areas and how do we communicate the vastness of space. So you know that let's say the square tiling of the floor, a two-dimensional flat space can be tessellated with tiles, with square tiles. And when you try to describe how much space is occupied, how large is your room, you describe how many space tiles, how many tiles are covering or enclosing the space. So for example, if I have this empty space and I placed 3 tiles along and 2 tiles across, then I have altogether 6 tiles, right? So it's very easy to calculate areas of rectangles. It's width times height, because by multiplying width times height, you count how many squares, how many unit squares fit into that rectangular shape. Make sense? All right, guys, so just that's a quick review. Why is the area of a rectangle height times width? Because height times width counts how many squares, how many unit squares, how many tiles are fitting into our structure. Am I making sense? Now, what is the area of triangle? Let's begin with a right triangle. A right triangle with width W and height H, it's 1/2 W times H. Do you understand why 1/2? Because it's half of the corresponding rectangle with width W and height H. Do you understand so far, guys? I went through this very fast. Do you understand? So it seems like I'm asking you simple questions. Whenever you think the question is very simple, ask yourself again. The area of a rectangle of, let's say, width 5 and height 3 is going to be 15. What is that 15? It's the 15 tiles that you will count inside of that rectangle, right? When you say length, if you say width is 5 and height is 3, you say that we have some unit tiles, the unit square tiles, and it is 5 tiles across and 3 tiles high. So altogether we must have 3 times 5 or 15 tiles. You understand? It's like in this picture, right? Look at it, 3 tiles and 2. So that means 3 tiles here, and then the next is another layer of 3 tiles, another layer of 3 tiles, and whatnot. Okay. So then if I have another triangle, the area, this triangle is not half of a rectangle, but here is what I can do. I can drop this height and I can build two right triangles. I have this big right triangles with that has width w plus w prime and height h, and I have the small triangle which is width w prime times h. I'm going to show that w prime is not important. So the area of the black triangle is it's the area of the big triangle, big right triangle, which is 1/2 w plus w prime times h, minus the area of the small red triangle. Yes, and I get again the formula 1/2 w times h. Do you have any questions before I move on? I'm reviewing it, guys, but I'm not. So now finally we are at the Pythagorean theorem. Pythagorean theorem. So it's a very famous theorem. I'm sure you know the statement: a squared plus b squared equals to c squared. How many of you know how to prove it? That's terrible, right? See, so you have the statement and it takes a second to prove it. Let's see if I will correct it, okay? So here is how we prove it. You understand? We're saying that that a squared plus b squared, the sum of the squares of the legs equals to the square of the hypotenuse. Why is that the case? Take this triangle and make additional 3 copies and place them as follows. You understand? You just rotate it. So it's a, next to a you place b, next to a you place b, right? And you obtain the structure. Are you with me? You understand what I did? So what is c squared? C squared is the area of that square that you see here, the inner square, right? And I'm going to calculate the area of the inner square twice. For one of them it's c squared, and the other is that it is the area of the big square. Look at it, it's also a square. It's a plus b is the length of the side. It's a square of a plus b. And then I remove the triangles, right? Square that, remove the triangles. Are you with me? Guys, you haven't lost consciousness just yet, right? Nothing so complicated. So c squared is the area of the big square, of the small square. And so what can I do? I can take the area of the big square, which is a plus b squared. It's a plus b times a plus b. It's a plus b squared minus 4 times the area of the triangle. It's the same triangle, so I subtract 4 times the area of one triangle, yes? So my area c squared is equal a plus b squared minus 4 times 1/2 ab. Now if I expand a plus b squared, it's a squared plus 2ab plus b squared. 4 times 1/2 ab, it's minus 2ab. So I get a squared plus b squared. Was it difficult? Do you understand it, guys? If I asked you to prove it without looking at it, would you be able to do it? Just take a right triangle, make copies and rotate it and form this structure. Yes? That's what you have to understand. If you remember forming the structure, now you see the area of the small square is equal to the area of the big square minus the areas of the triangles. And I know how to calculate areas of triangles, right? This triangle has area b times a times 1/2. And there are 4 of them. So together they have combined area is 2ab. And if I have a plus b squared, it has the 2ab, and I subtract the 2ab and I get a squared plus b squared. Proof complete. You're welcome. Now, the Pythagoreans were those people that made the discovery. They were famous for the saying, all is number. And by that, I think they meant that every segment of space is in proportion to every other segment of space, guys. And if you find measurement boring, then you are not looking at measurement correctly. The entire theory of relativity and quantum physics, they arise out of the problem of measurement. Okay, so both quantum physics and the theory of relativity and many other things are really problems in measurement. You understand very deep, profound things about the nature of your existence, of where you are, and of space and time by understanding what is measurement. So here are some questions that seem to us rather sensible. When I say all are numbers, I can ask you how tall are you, right? And you can take, and I'm not sure what you prefer. You can take a meter stick or a yardstick, whatever you like doing, right? And you can measure how tall you are. How long have you studied for this class? I can ask that, right? And I don't mean in this class. I mean in general, right? And maybe you can give me a nice number which is 0, right? Hopefully, if it's not 0, then it's a number that you might be worried. How do you communicate it? Am I asking something meaningful? And then if you're in the car, how fast are you driving? How much do you weigh? And if you don't like those questions, here is another. Is the future determined? Is there such a thing as cause and effect? Is time travel possible? Those are all related questions at the end of the day to the statement all is number. Okay? And these questions take their root in the problem of measurement. And nice that we mentioned root. So here, guys, here I take a line segment and I can ask how long is this line segment? And I measured it in centimeters because no normal human being will use inches. So it is 14 centimeters, and there is this extra segment of length. And what is that? Well, that happens to be 4/10 of a centimeter. So it's 14 centimeters, and then I need to slice the centimeter into equal parts. It's 4/10 of a centimeter, right? So that means that this length is a fraction because it's 14.4. It's 72 over 5 centimeters long. You understand? So when you say all is number, in a sense, you're just saying I can take a line segment, a piece of space, and I can measure it. Yes? So every line segment can be measured. Do you agree with that statement, guys? Every line segment, I can measure it. Write in the comments if you agree. Okay, interesting. Interesting, makes sense. Can you measure every segment of space? So you see here, I just took a segment and I was fortunate enough to be able to measure it exactly. I was able to calculate that its length is 14.4 centimeters or 72 over 5 centimeters. Okay, that means I take 72 centimeters and I cut that somehow proportionately into 5, and 1/5 of 72 centimeters is my length of the stick. Okay, yeah, so you say you could. Okay, so here is, let's see if you would understand what is an irrational number, guys. So here is a triangle that has length 1, leg is 1, the second leg is also 1. What's the measure of C? What's the length of C? Could you tell me? Write in the comments. What is the length of C? Careful, Stephen, right? Remember, it's on a triangle. Is it 2? We just figured out the Pythagorean theorem. Alexa, you says 2 squared, but that's 1 squared plus, no, careful, guys, right? What's the length? Come on, Pythagorean theorem, you said you understood it. What's the length of C? Thank you, Ying, thank you, Lisha. What's the length? Come on, write something, guys. Steven, thanks. Thank you, Dragon. Good. So this number, guys, is this. By the Pythagorean theorem, I can figure out this number as follows. The sum of the squares of the legs is equal to the square of the hypotenuse. Yes? So C squared, the length of the hypotenuse, is 1 squared plus 1 squared, which is equal to 2. 1 squared plus 1 squared is 2. Are you with me? So that means that C is a number that when multiplied by itself equals to 2. And many of you wrote the answer therefore is square root of 2. But square root of 2 is tautology. I'm just saying a number multiplied by itself equals to 2. You understand? When I say square root of 2, what you wrote in school, that's not in some sense not an answer. Because you're just saying, oh, the answer is a number that if you multiply that number by itself, you get 2. That's what square root of 2 means. Good? So here is here the question is there such a number at all, right? Is there such a number? What do you think? Is there such a number that if you multiply it by itself, you get 2? Yeah, so think about it, guys. I'll be right back, okay? Write the comments. I will be back in 1 minute.
We'll shuffle 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
I'm glad that some of you remember how to count to 7.
55, I'm gonna press that.
Okay, where is that coming from? Well, only 3 comments. I am definitely very happy that you remember how to count to 7, my friends. But here we are trying to figure out this thing. So let's suppose that we have such a number. Are you here, guys? Let's suppose we have this number. And the number, because I don't know what it is, that it's a fraction. So it's going to be m over n. And any fraction can be reduced to simple terms, right? To simplest terms. So let's say 3 over 6 is a fraction of 2 integers. I can reduce it so that it's 1/2. In other words, I can assume that the greatest common divisor of numerator and denominator is 1, that they don't have anything that I can factor and simplify. Yes? Good. Now here, guys, let's see here. Let's see. So then if I square this number, right? If I square this number, I get 2. Good. Square this number, you get 2. And squaring this number is m squared over n squared. And if I multiply by n squared both sides, I get that 2n squared is equal to m squared. You understand? Up to this line, guys, what I'm doing. And so that means that 2 divides m squared. You write it as 2 vertical line m squared. 2 divides m squared is how you say that. And that means that 2, in fact, divides m, which means m is equal to 2 times some other integer. And then I return back to this equation. I square the 2 times this integer, the m, and I get 2 times n squared. So I have 4k squared is equal to 2 times n squared. I can again, now I divide everything by 2, and I see that n squared is equal to 2k squared, which means 2 divides n squared, which means 2 divides n. I hope you were able to follow that. But I just assumed that m and n were reduced to least common, so that they were reduced to simplest terms. And now I observe that 2 still divides m and n. And this is a contradiction. Do you understand? What I do is I find if there is a fraction that exists. Are you with me, guys? If a fraction exists, then I can reduce it so that nothing is in common. I cannot cancel it anymore. And then I go through this discussion, and I see that somehow 2 still divides both numbers m and n. And that's a contradiction. This means that root 2 cannot be a fraction. It cannot be any of the numbers that we saw before. This thing is not going to work. And of course, I cannot see your faces, but you know that the next thing that I'm going to say, well, before I say that, if you press, you press something in the calculator. You press in the calculator, and this is what you get. Is this root 2? This is not root 2. This number multiplied by itself will not give you 2, because this number is a fraction. You can convert it. It's a fraction. You understand? It's this number over 10 to whatever power. That's not root 2. Are you with me? And no matter how many digits you write, you are not writing root 2, because what you wrote is a fraction. And the same thing holds for root 3, root 5, root 6. For most numbers, when you try to calculate the roots, you will observe it cannot be a fraction. So this cannot be the answer. And of course, when I cannot see your faces, but I did see faces before. I happened to teach at some point thinking mathematically or something equivalent to it. And I look at their eyes and, my God, why do you care? And my explanation was inspired by you, my dear, wonderful students. You don't care? Then you would not mind if I pick a huge brick, hold it 5 units over your head, and drop it. You should not be upset. Logically, it's the same thing. You understand? If you do not care about root of 5, you should not mind if I pick a huge brick, hold it 5 feet over your head, and let it go. Now let me explain why. So the brick, in t seconds, the brick will travel 16 t squared feet. Okay? So the question is, am I liable for what will happen next? Am I to blame for anything? So let's drop the brick 5 feet above your head. Will the brick hit your head? The equation, basically the brick, if it hits your head, there is a particular moment of time where it comes in contact with your skull. And so that moment of time is 16t squared. It means that 16t squared equals to 5. And that means that the time of impact is root 5 over 4. It is exactly root 5 over 4. So if root 5 does not exist, that means that there is no moment of time where the brick comes in contact with your head. It will never touch you. So either of two things, either nothing will happen to you if I drop the brick, or if your head gets smashed, it's not because the brick fell on your head. It has nothing to do with me. There was no, it did not cause your head to splatter. It's just coincidental, right? It just, I dropped a brick, and just at that moment of time, your head caved in. At any rate, I did everything I could. You cannot blame me. So this is the implication, right? And if you realize that implication, you might start thinking, is it a serious thing or not? It's really an implication about cause and effect. It's really an implication about your understanding of how things work. Okay? So if you believe that there is a definite moment of time where something is supposed to happen, there is a moment of time where the brick touches your head. That means that moment of time is root of 5 over 4, right? So what is root of 5? Root of 5 is not a number like that. It's not something that if whatever you write, it's an approximation, but it's not It means this number, if you square it, it kind of behaves like 2, but it doesn't give you a perfect 2. So, but in here, it's an absolute. Either there is a moment of time, which is root of 5. Either there is exactly a moment of time, or there is no moment of time. It's an absolute. Okay? It's like the brick is kind of close to your head, but that doesn't matter. I mean, is the brick touching your head? So there is, and that's the last thing I would say, might be extra credit. So if you actually imagine the existence of this thing, you can find an approximation. Okay, so let's say find an approximation to root of 2. Here is what I can do. Look at it. Root of 2 is just something, right? So it's equal to 1 plus the something minus 1. Doesn't seem like I have achieved anything at all, right? Now look at it. I can then do this favorite thing. You see, it's root of 2 minus 1. I multiply by the conjugate. Multiply and divide to not change anything. Numerator then becomes 1. And denominator is root of 2 plus 1. And then I try to make it look like the original expression, like what I put here in this blue square. So I write 2 plus root of 2 minus 1. You see, because then I have, this box is the same. So I want it to be minus 1. I have a 1 here, I add another 1 to it, and that subtracts a 1 from root of 2. And then I see that this box, guys, you see this box is then equal to this full thing. So this box is equal to this full thing. This guys, is equal to that. But it's also equal to that. So you see that it's the circle, it's inside of itself. And that allows me to quickly generate this continued fraction. Root 2 is 1 plus 1 over 2, 1 over 2, 1 over 2 forever. So the calculator estimates this is the number that the calculator estimates. And let me show you how you can use this tautology to get this estimation. Look at it. First number I try is 1/2. Then I'll plug 1/2 into 1 plus 2 1/2. Then I'll plug this entire thing into 1 plus 2, and this entire thing is here. And I will simplify it so it's not as scary to look at as here. So my first approximation is 1 plus 1/2, it's 1.5. Next approximation is I put this 1/2 in here. So it's 1 plus 1 over 2 plus 1/2. I multiply numerator and denominator by I multiply the numerator by 2, and yes. So so I made a mistake here. It's interesting. So I multiply this by 2 and this by 2. It should be actually 5 here, but yeah, it's a stable thing. So I actually I made a mistake here. You see. So so I plug here. Basically what you do is you take 1 over 2 plus, here is what happens. It's 1 plus 1 over 2, that's first estimate. Second estimate is 1 plus 1 over 2 plus 1/2. And I multiply everything by 2. So what I get is 1 plus 5 divided by, sorry, 1 plus 2 divided by. I multiply this by 2 and this by 2. So it's 2 divided by 5. Next estimate is 1 plus 1 over 1 plus 2 divided by 5. So I multiply it by 5, so it's 1 plus 5, and 5 times 1 is 5, plus 2 is 5 plus 2 is 7, 5 of 7. 4 is 1 plus 1 divided by 1 plus 5 over 7. And that would be 1 plus 7 over 7 plus 5, and so on. Okay, and that will give you that will give you an estimate of the root. So it's actually stable. If you take something similar, you still, I made an error, I made one mistake, but you can still, even with the mistake I made, you can see that you are gaining more and more decimal places. Good. So this is something very beautiful. It says that something like, well, deep meaning, I think, is tautology carried out to infinity. You could have come up with this argument if you think this particular way, guys. So then I want you to try to see if you can estimate root of 3, root of 5, and root of 7. Have a good day. If you're not staying for office, I will stop recording right now.